tool, a mathematical tool that has applications in many different fields of science, right? In particular, here we are going to use one of its applications. And the application is going to be to solve initial value problems, right? But not just any initial value problem. The differential equation on the initial value problem is going to be linear again, and with constant coefficients and homogeneous. So you would say, so what are we gaining? You already know how to solve those, right? So in chapter 4, homogeneous, linear, with constant coefficients. I mean, how do you solve those? Let's go back to our chapter 4. Characteristic equation, roots, linearly independent solutions, C1 plus, then you apply the initial condition, find the C's, but no. So we already know how to solve those, right? Now, but we recall about those linear, homogeneous differential equations with constant coefficients. The order can be very large, right? Think about order 4, order 5, right? 4 derivatives or 5 derivatives of the unknown function appearing in the equation. Then the characteristic equation is a polynomial equation of degree 5, 6, or higher, and find the roots might be a difficult problem, right? Although you can always approximate because you add all these other tools. But it might become time consuming, and also once we have the linearly independent solutions, you have C1 plus C2 plus a lot of C's to be found using the initial conditions, right? This method, or this Laplace transform, provides us of a quicker way to find the solution, right? For this type of initial value problems. But keep in mind that there are restrictions in order to apply this Laplace transform that we are going to present in chapter 9 to solve initial value problems. What are those restrictions? The differential equation has to be linear. Second restriction, constant coefficients. Third restriction, homogeneous. So once you have that, an initial value problem where the differential equation satisfies those 3 restrictions of being linear, constant coefficients, and homogeneous, then the Laplace transform is going to give us a nice tool to find the unique solution of the initial value problem, following always the same steps as we will see in this chapter. So the first thing we have to see, what is the Laplace transform? Well, it's a transform, so it transforms things. I mean, that's the first thing. If I don't know anything about this, and they tell me, I'm gonna talk to you about the Laplace transform. Oh, okay, so it's something that is going to transform things. So, what does it transform? Functions on the variable t into some other function. On the variable s. So, you're given this, you apply, this is the symbol we are going to use for the Laplace transform, and the script L for Laplace. You apply the Laplace transform of this, and you come up with the Laplace transform. The Laplace transform of the function f has a new variable s, right? Think of, for the sake of simplicity, that the function f of t has a domain. T is time. Start measuring time t equal to 0 now. Forward, that the domain of the functions ft we're going to take the Laplace transform of is positive real numbers from 0 to plus infinity. Time. Okay. So now, how do you compute? What is the? Well, transform, the Laplace transform of a function little f t is going to be defined as a function of s in terms of one of those integrals that you saw in calculus 2 towards the middle. The so-called, remember those improper integrals? Improper integrals, there were different types. This one here that we're going to use to define the Laplace transform is going to be one of those for which the upper limit is plus infinity. And where are we going to integrate this? That's the basic definition of the Laplace transform. Whenever, remember, let's go back to our calculus 2. Whenever you have an improper integral, what is the key question to answer? What was the key question to answer?
Is the divergent convergent?
So for the Laplace transform to exist, it has to be convergent, right? So we're looking for functions for which this converges. So meaning the fact that it's improper integrals, those improper integrals in general, as we saw in calculus 2, they could be convergent or divergent. It means in the context of the Laplace transform that there might be functions, these ones, for which if this improper integral converges for values of s, the Laplace transform exists. There might be functions, like some functions of t, for which this improper integral diverges, and therefore we will say that the Laplace transform does not exist. We'll see examples, right? But this is gonna be, it's not gonna be a main concern for us. We're gonna assume that we're gonna be working with functions f of t for which the Laplace transform exists, right? But there are, keep in mind, there are functions little f of t for which the Laplace transform. I'll give you an example. If I give you this function, like that, right? T squared. Then that's not have a Laplace transform. Or in other words, the Laplace transform of this function does not exist. Or in other words, if we plug this here, we get an improper integral that it will diverge. So keep that in the back of our minds, that there are functions of t for which the Laplace transform doesn't exist. But in this chapter, we're going to be working with functions for which we will be able to find the Laplace transform, meaning that the Laplace transform exists, meaning that the corresponding, when you plug here f of t, the corresponding improper integral converges. Okay? Now, if I take this function, constant function 1, that's a function of t, right? Constant. One. Horizontal line being the graph. Level 1 on the y axis, on the vertical axis. That's a nice function. Does the Laplace transform of that function exist?
Yeah.
What do you have to do? Plug one here. Now, how would you continue? Remember, now it's a calculus 2 problem.
You replace the infinity with b and then take the limit, correct?
So this is b. To check whether it converges or diverges, we look for this limit. We replace the infinity with a b, and we take the b. Here you get, let me just put the minus st times 1, well, 1. So, dt. We put this in a bracket, because now we focus this, this is now an definite integral, right? How do you find that? What is that equal to?
Is S just a constant?
Hmm?
Is S just a constant?
If you integrate with respect to t, the other variable is like a constant. So,
You have to multiply by S and divide by S.
what's the antiderivative? Right? Then you plug the limits. Remember the fundamental, and then you take the limit when b goes to infinity. Right? The antiderivative with respect to t. Now, what's the next thing we need to do before we take the limit? You plug the values, remember? T equal to b minus this t equal to 0. So what do you get? Let me just do it. At t equal to b, you get this minus, at t equal to 0, e to the 0 is 1. Now, look at this. You get 2 minuses, so minus, minus. And now we take the limit, right? Let's take the first term in the bracket. And let me ask you, b, s is positive, so it's b. What's the limit as b goes to plus infinity of that first term?
0.
What is it?
0.
0 because of the negative exponential. So let me just cross it out. The second one does not depend on b, so it's like a constant. The limit of a constant is the constant. And this shows that the constant function 1 has a Laplace transform.
So it's not like, so it's not just ft alone, it's like the two of them together. Like,
What do you mean the two of them?
It's like, well, I
Plus.
like,
Thank you.
if I put like the f is one and like a series, I know one is a divergent in a series, so I thought like it would be that.
No, that's serious is this improper integral, right? This is an improper integral, and then you put the 1 here against this, you integrate, See, if it converges, it does converge to what? To 1 over s. That's the Laplace transform of the constant function 1.
So this would work for any constant function? The same
Good
thing?
question. If the Laplace transform of the function 1, we just found it to be 1 over s, what do you think the Laplace transform of the constant function 2 is going to be?
2 over S.
Okay.
What do you think the Laplace transform of the constant function minus 11 is going to be?
Over S.
And you can show it
Okay.
clearly. So think about it. I mean, if you, the constants, you can pull them. And that's what it does, because look, from everything we know from calculus, from calculus 2, if you get a constant and an integral, you can always put it here. And then you're left with the Laplace transform of 1, which we have found. So the constant, then you multiply by the constant. That's it. So this is the first Laplace transform that we found. Very important. The Laplace transform of the constant function 1 is 1 over s. And as we just said, for any other constant, is that constant divided by s. Laplace transform. Okay? Let's go one step further. What do you think? Do you think I take t? Now remember the graph of the t is a straight line, 45 degrees going through the origin, right? On the x. So for that, we're gonna have a t, and things becomes a little bit more complicated, right? Ooh, 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 ooh. This is no longer this. How will you continue this problem? Trying to find out whether the Laplace transform of that function t exists.
By parts? Can we do it by parts?
by parts, it will take more work, blah, 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 but then you follow the same steps. Let me put these dots, boom, 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 and the light comes. What's the Laplace transform at the end? Yes, it does exist. 1 over s squared. And
And then if you have like the t multiplied by a constant, would that also be at the top? Would that work that way?
good question. So, what if rather than just the function t, I have 5t? You have 5. That's a constant. So, what do you think you're gonna get? 5 over s squared. Same as for the constants.
So in the exam, you could just do the dot, dot, dot.
Yes, you can. I'm not gonna test you on finding this is something that you know how to do from Calc 2. These are improper integrals, computing an improper integral. That's something that you learned in Calc 2 and you were tested on Calc 2, that you know how to do it. I don't wanna get into this. You put the dot, 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 dot. Use tables, as a matter of fact, that you can bring to the exam too.
So we will be expected to solve the transform, the inverse transform. We'll have to memorize this table from the book.
Not memorize, you can bring a copy of that. No, I don't want you to do improper integrals. Improper integrals, to do improper integrals is to do integrals. This course is not on integration. That was something that you learned in calculus. So I won't be asking you to compute an improper integral whether it converges or diverges, no. Okay. But know the definition. That's how you define the Laplace transform in terms of an improper integral, right? Remember, for an FT, that's the original definition. And like we said, from what we know are improper integrals, some of them converge, some of them diverge. So according to that, there will be some functions, f of t, for which the Laplace transform exists, converges, and some other ones for which it doesn't. I gave you an example up there, e to the t squared, for which the Laplace transform doesn't exist, right? But for all practical purposes in this class, we will assume that you are going to be dealing with functions of t for which the Laplace transform exists. How would you compute them if you have to compute them? Not by hand, just using tables, okay? Using tables like the one on page 500 in chapter 9, of which you can bring a photocopy to the exam. And properties of the Laplace transform that we're gonna see here. So table and properties. We're gonna get to those properties, very important properties of the Laplace transform that they will help us on the final goal on this chapter 9. What was that goal? Using the Laplace transform to do what? Solve initial value problems with some restrictions, right? 3 restrictions in the differential equation of the initial value problem. The differential equation in the initial value problem has to be linear with constant coefficients, number 2, and homogeneous. Let me give you an example. Well, before that, so we got the definition, now we want properties. Properties of the Laplace transform, specifically, not all properties, the ones that they are going to be useful to us in solving initial value problems using the Laplace transform. Okay, so let's go here. Properties of the Laplace transform. And the first one we're going to see is the so-called linear property. And it's so properties. The so-called linear property. What does this linear property? Let me illustrate. Remember what we said? Now, remember, on what we did before that, we found that the Laplace transform of the constant function 1 was, and the function t, 1 over s squared. Now. Knowing those two Laplace transforms, what would you guess would be, from everything we've seen, after you multiply by constant, the Laplace transform of that? Negative 3 over s. What else? Plus 8. 8 what?
Over s squared.
How did you get this? Which is correct. You break it, right? You argue as follows, right? Correctly, as follows. The Laplace transform of this plus this is the Laplace if the Laplace transforms of each exist, is the Laplace transform of this plus the Laplace transform of that. Now, what about the constants? You can pull them out. So it would be minus 3 times the Laplace transform of 1. What? Plus 8 times the what? The Laplace transform of t. That's it. That is what is called the linear property. In general, how would you state that property? Like this. If you have, going here, right? N functions of t, n. Now, not just 2, but many, right? Dot. And the last one, right? And if the Laplace transform of each exists, if you multiply by a constant each one of those, then the Laplace transform of this is nothing but take the first constant and multiply by the Laplace transform of the first. Plus. Pull out the second constant, Laplace transform of the second. Remember, we are assuming that each one of these Laplace transform exists. Plus dot, plus the last constant, pull it out, and take the Laplace transform of it. That's the linear property. And this linear property, in a sense, to prove that this linear property holds, it follows from the definition, right? And the properties of the intervals in proper intervals. Remember those properties from Car 2? Any questions? This is very important property, right? And this is an illustration of how to use it, right? Now, what else? About this Laplace transform.
Question? You said earlier that you showed us t squared, like the
T
Laplace.
squared?
Yeah, for t
What's-
squared, the Laplace transform for that one. And you said it diverges.
No. E to the t squared.
E.
That one diverges.
Oh, okay.
Not t squared. E, that's, you see,
So-
think about it, right?
Mhm.
T squared is like a parabola, right?
Mhm.
E to the t squared, it shoots. It's an exponential growth.
Mhm. Okay.
That's why the difference between the two. If the growth, think in these terms, if the growth of the function f t is not too big, exponential or then the Laplace transform exists. But if the growth is larger than exponential, that's what larger than exponential is, because exponential is this, or a constant here. When you put the square on the exponent here this way, this is much larger than exponential growth. And whenever the function grows, or the growth of the function is larger than the exponential, that's when the Laplace transforms.
Okay, so then when you have like 8 to the t squared, what does that look like? Would that be like
If this
8
would be
over
good question,
s
so
cubed? Is that?
it will be 8 times the Laplace transform of t squared, right?
Mm-hmm.
The Laplace transform of t squared is this.
Okay.
So it exists this time.
Okay. And then what about for like everything after that?
For?
Like t to
Now think about the
third.
pattern.
Exactly. So would
What
it be
is
like
this-
3 over
so-
s to the 4th, and then like 4 over s to the
There
5?
you go.
Okay.
For t cubed, 3.
Okay. All right.
Now, almost. Because it's not just a 3, it's a 3 factorial.
Oh, okay.
3 times 2, 30.
Oh, okay. Okay.
Right? It's
Okay.
factorial on that term. Not just the 3, but the 3 factorial. Those are the Laplace transforms of the integer powers of t. And that's one of the formulas in the table on page 500 that you can bring to the test. Any other question? So, this is a very important property, linear property. And here you have an illustration of how to use it, right? If this would be a 4th, then this would be is 5 or more, and the exponent would be a factorial still there, but it's a 4 factorial, right? Now, what is 4 factorial equal to? 4 times 3
24.
times 2. Those are that's the concept of factorial, right? First property. Second property we're gonna see here. Let's see the second. This is a very important property also after the linear one, which is really, really important. But it's a property that relates, and this is important because of what we want this Laplace transform to do for us, right? Solving differential equations. So, the differential equation involves a function and the derivatives. So it might be nice to have a property that relates the Laplace transform of the function with the Laplace transform of its derivative. That's the property. Provided we put this in a box because that's a problem. Provided you start with a function ft for which the Laplace transform of the function and its derivative exist. Then, are they related? Yes. By what? By this formula. The Laplace, this is how you read this formula. The Laplace transform of the derivative of function is equal to the variable s times the Laplace transform of the function minus a constant. What's the constant? Evaluate the function at 0, the original function at 0. So let me just go here. Right? That is the derivative of what function? T to the 4, right? So, look at that formula. This is the derivative, this is a function. So this property says that the Laplace transform of this is equal to what? S times the Laplace transform of this minus, that's the f at 0, so it's 0 to the 4. Now, but we know how to, what are those, right? Remember? Powers, the 4 you can pull it outside, so this is 4 times. What is the Laplace transform of t cubed? 3 factorial over
S to the 4.
equal. So let me just put a question mark. S. What was the Laplace transform of this? 4 factorial over? And that's 0. Now look at this, S divided by S2, this will cancel one of these and this becomes a you multiply 4 times 3 factorial, it becomes what? 4 factorial. Now look, yes, they are equal. They should by the property. So this is an important property number 2. That's the one that relates. When both exist, the Laplace transform of the derivative with the Laplace transform of the function. By this formula. That's something to remember, right? Those properties you need to remember. Now, any questions? Now, so these are the first 2 very important properties of the Laplace transform. So let me, with these properties, we're ready to solve some initial value problems already, right? Simple ones, right? So this is a very simple chapter 2. Chapter even, no, 2, 1, 1, 2, 2, 1, 2. Linear, order 1, constant coefficients, initial condition 1. We know how to solve this already from chapter 2. The question would be, with everything we know so far about the Laplace transform, which is chapter 9, how would you solve that using the Laplace transform? Now, that's what we are going to do next, right? I'm going to illustrate this, how to solve this using the Laplace transform, right? With a simple initial value problem. But once you've seen this, one, how to be solved using the Laplace transform steps, step by step, any other one is following the same steps.
So when you get a function that diverges when you take the limit, that means you can't apply the right? Okay.
You cannot, certainly,
Okay.
because
Yeah.
for this method to work, you need the Laplace transforms to be converted.
Okay.
So if somewhere along the way you have a function of t for which the Laplace transform doesn't converge or diverges, and then we have a problem, and as a consequence we say, well, the technique or this method cannot be applied.
Okay.
So, let me show you quickly the steps that you need to follow, right, in order to solve initial value problems using the Laplace transform technique, which is the main goal in this chapter, right? So, the first thing you do is take the Laplace transform of the differential equation. So it would be a linear property. Take Laplace transforms on both sides. It is true. Think about the definition we gave the Laplace transform in terms of any problem. What is the Laplace transform of 0? No. Remember, you plug 0 into the improper integral, but any 0, 0, 0, 0, 0. The Laplace transform of 0 is 0. So on the right hand side, if I take it, you get 0. On the left, I get the Laplace transform of y prime, which by property 1 is this. Move this, plus the Laplace transform of y. And that's equal to 0, right? So what have I done? Like 2 things in one. Took the Laplace transform on both sides, use the linear property and property number 2 on the left hand side to get that.
Okay, so you may answer this later, but typically we'll also get like a differential equation that has a double, like,
Higher derivative.
yeah, a higher derivative. So then, is there another property for that?
There will be
Okay.
another property.
Thank you.
That would be the next number.
Okay.
3, to deal with higher derivatives, precisely because of that.
Okay.
So far, with these two properties, we can only deal with the first derivative.
Mhm.
So now, look at this. After you do this is an algebraic equation on the Laplace transform of y. Algebraic equation, because if I take this term together with this, what do you get? S plus 1 Now, what is the initial condition? That's where I'm gonna use it. What is this equal to? Now the next goal is gonna be to solve, to isolate the Laplace transform of y. Any questions? So, solve this algebraic equation, remove the 1, divide by 8. Right? So, what have we done so far after those steps? We came up not with the solution. The solution would be y of t. We came up with the Laplace transform of the solution, of the unique solution. So I need to go backwards. From the Laplace transform of the solution, take the inverse of that, and find the solution. And usually this last step can be done using properties and tables. And you will find out, and you can take a look at table in page 500, right? You go to that table, and you look at formula number 2, you see for this, in the second column, for these 5 functions of S, the inverse Laplace transform is this function of t, e to the minus t. That's the end of the problem, because this is the unique solution to the initial value problem, as you can check yourself. Right? The derivative of this plus this is 0, and when you evaluate this at 0, you get 1. That's the unique solution, because we know there is a unique solution from the theory that we learned in chapter 1.
We just match it to the table.
For the inverse,
Right, yes.
you use the tables. In this case, you use the table. There is a formula on that table, among others, number 2. Boom. Use that to get the inverse. And the inverse, the table on formula number 2 in the table gives you that the inverse is e to the inverse Laplace transform. That the inverse Laplace transform, that's what this means, inverse Laplace. Remember minus 1? Of this is this function. That's it from the table. And that's the end of the problem, because that's the unique solution. That is the unique solution as a function of t of the whole initial value problem. Any questions? So, this is what we need to do. That's the goal. That's what we are going to do. But not for this simple one, but the second, third. So what's the property that we need besides this one for the higher derivatives? That's number 3. For any derivative, you get this formula, which in a sense this generalizes this, makes it. So what is this? Well, it's s to the n times the Laplace transform of function eta minus, that's property number 3, s to the n power n minus 1 times the value of the function at 0 minus s to the power n minus 2 times the value of the first derivative at 0. Let me do one more. Minus s to the n minus 3 minus, etc., dot, 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 minus s
0.
derivative 0 and minus the n minus 1 derivative. That's it. That's it. And this is a formula or the property of the Laplace transform that holds for any positive integer and any higher derivative. So it could be, you get many formulas here, many properties at the same time. One for n equal to 2, 3, 4, 5, 6, all the derivatives. Now, in particular, you can easily check that number 2 is just this, when n is equal to 1. So from now on, you can use this one, number 3, because it's more powerful. That's for all the derivatives. And that's property number 2. The way to look at this property number 2 is the property that relates when they both exist, the Laplace transform of the nth derivative with the Laplace transform of the function. Because the rest of the stuff on the right hand side are powers of s and values of the function and its derivatives at 0, the initial conditions of the initial value. That's it. Now, so for instance, if I change this to this, right? Second derivative. How would you find the unique solution? Following the steps. Remember what we just did? Now I need another condition, right? Because it's second derivative. So. How would you follow the same steps as we did before to solve this one, to find the unique solution? Well, if you take the Laplace transform and use property number 3, this is what you get. Plus Laplace transform of y. You know that the Laplace transform of 0 is 0. What would you do next? Here, this in this bracket, we use that number 3 for the second derivative. What would you do next? Use the initial conditions, right? What are the initial conditions? Where is y at 0? 1. Where is y prime at 0?
0.
0. So that's one. Now, what was the next thing we did?
Find the Laplace of y.
Hmm?
Solve for the Laplace of y.
For the support. So if you do that, if this is algebra, just move, boom, boom, this is what you do. So if this is an algebra step, solve that equation for the Laplace transform, that's what you do, right? Manipulate, isolate the Laplace transform, right? You put these two together, this, we move it here with positive and then divide.
Question. So do we have to have an IVP in order to solve using the Laplace? Yes.
It has to be an IVP.
Okay. Okay.
So once we're here, there is one last thing we need to do in order to get the unique solution of the IVP. What was that step? Table to get the inverse, right? So now, for those of you who have the book, read the table. What do you do? Well, we go to that table on page 500, right? And we look on the second column, on the last column, functions of S, anything that looks like that, like this. And you see number, formula on that table, number 4. If you do number 4 when P is 1, that's what you get there. And if you look at the previous column, on that number 4, what's the inverse? The cosine of T. And this, cosine T, the function cosine T, just the cosine of T. That is the end of the problem. That's the unique solution of the whole initial value problem. Do you see that? By going back to your question, right?
Yeah.
You have, then you can use 2, you use 3.
Yeah. Okay.
But the idea on how the step is always the same.
Yeah.
Same step. Any questions? So let me stop here for today. Let me just give you some homework. Just start working on this chapter.
More.
Well, it's too early for. Let me just give you the first homework name. No homework